This video will include homework solutions to section 8.1. Section 8.1 is an introduction to sequences. I'm going to start with problem number 10. It's even, and so the answer is not in the back of the book, and it's the most challenging problem in that section of the homework. It says find a formula for the general term a sub n of the sequence, assuming the pattern given continues. So this is 5, 1, 5, 1, dot, dot, dot. So we have a sequence whose terms are 5, 1, 5, 1, 5, 1, and we have to come up with a general term. Now remember, this is a sub 1, and this is a sub 2, and this is a sub 3, and this is a sub 4. In other words, when we plug in a 1 and a 3, we want a 5. But when we plug in a 2 and a 4, we want a 1. So if the term is odd, one, 3, 5, then 5. If the term is even, then we want a 1. So it's going to take a little bit of thinking, and then a +2 or a -2, depending on the value of n. So if n is odd, we want this to be a +2, but if n is even, we want it to be a -2. So we can multiply this by -1. Now, we need a power here, so we'll put n first. We'll start with that. Now, what happens when n is 1? 1 is odd. So we would have 3 + 2, -1 to the first would be -1. That would be 3 - 2. That would give us a 1. That's not what we want. So we need it to be n + 1. Now when n is 1, this is 1 + 1, that's 2. -1 squared is going to be 1. 3 + 2 is going to be 5. A sub 1 would be 5. When a sub 2 is asked for, however, we would have 2 + 1. 2 + 1 is 3. -1 to the third, -1 times 2, -2. 3 - 2, that gets us our 1. So this is our term, our general term for question number 10. Questions 11 through 34 say determine whether the sequence converges or diverges. If it converges, find the limit. So we can take a look at a general strategy here for something like problem 14. And in problem 14, they tell us that a sub n is equal to n cubed divided by n + 1. And they want us to talk about convergence or divergence. Now, we only have a definition, right? That's what we have in our toolbox to help us with convergence or divergence. We have the idea that says if the limit of the function equals L, then the limit of the sequence equals L, right? That's one of the theorems we have. So we can take a look at this, right, as a function and see if it's convergent. And if the function's convergent, then we would know that our sequence is convergent. So where are we going to go here? How are we going to start this? Well, we're going to take a look, right? We're going to take a look at a function that looks like this and see what that function would give us if indeed we were to take its limit as, in this case, x goes to infinity. So we're going to consider f of x equals x cubed over x + 1. And we're going to look at the limit as x approaches infinity of x cubed over x + 1. Now, that turns out to be infinity divided by infinity, which means we need to use L'Hopital's rule to evaluate this limit. Remember, L'Hopital's rule says if you have infinity over infinity or 0 over 0, then the limit of the function is equal to the limit of the derivative of the numerator, which would be 3x squared, divided by the derivative of the denominator, which would be 1. And here, then, we would get that this limit as x goes to infinity, this is infinity over 1, this approaches infinity. So going back and looking at our theorem now, remember our theorem says that our functional behavior is going to be similar, right? Similar to the behavior of our sequence. And so in this case, we would say then the limit as n goes to infinity of n cubed over n plus 1 equals infinity, which means this diverges. Another way we could evaluate this is we could have just said, well, let's take the limit as n goes to infinity of n cubed over n plus 1. And we could have used that idea from Calc 1 where we divide the numerator and the denominator by the highest power of n found in the denominator. That would give us n cubed divided by n. The highest power of n in the denominator is n to the first. And we would have this. Now this simplifies, of course, to the limit as n approaches infinity of n squared divided by 1 plus 1 over n. And as we evaluate that limit, this goes to infinity, this goes to 0. And so this therefore approaches infinity. And again, we would have that this sequence diverges. So there's 10 and 14. If we take a look at problem 22, right, 22, this gives us a sequence a sub n equals cosine of 2 divided by n. And if we look at the limit as n approaches infinity of a sub n, that's going to be the limit as n approaches infinity of cosine of 2 over n. Now, we can rewrite this as cosine of the limit as n approaches infinity of 2 over n, because cosine is a continuous function. And that gets us the limit as n goes to infinity of 2 over n is 0. That gets us cosine of 0, and that equals 1. So this converges, and it converges to 1. When we get to something like 25, here we have a sub n equals cosine squared of n divided by 2 to the n. And so when we take a look at this limit, what we have to do is think about the relationship between cosine squared of n and 2 to the nth power. Sorry, there's a little glitch there in the video. The internet cut out there. So we're back together here. So on question 25, we're going to have to look at this function, and we're going to have to think about the fact that cosine squared of n, cosine squared, so it's squared, right? Because this is equal to, remember, this is cosine of n squared over 2 to the n. What do we know about cosine of n squared? Well, we know cosine is always less than or equal to 1. And since we squared it, it's always greater than or equal to 0. So we're going to use the squeeze theorem here to talk about this problem. We're going to say, okay, if this is the case, this is the relationship between cosine, then we can put a 2 over n here, a 2 over n, or 2 to the n, pardon me, and a 2 to the n here, and not change these inequalities, because 2 to the n is always positive, so this inequality will hold. So when we take a look at the limit of this function and this function, the limit as n goes to infinity of 0 over 2 to the n, that's going to be equal to 0, which, by the way, is also equal to the limit as n goes to infinity of 1 over 2 to the n, because 1 over 2 to the n is 1 over infinity. That's also 0. So this is 0, and this is 0 when we take their limits, right? When we take the limit here and we take the limit here. So by the squeeze theorem, when we take the limit here, we're squeezed between 0 and 0. Therefore, the limit as n goes to infinity of cosine squared n over 2 to the n equals 0. And so to get this answer, we have to use the squeeze theorem. Barring any more internet hiccups, we'll see if we can get rid of get a few more problems done here, and then we'll be done with section 8.1. What about something like 45? Determine whether the sequence defined as follows is convergent or divergent. So we have 45, and here we have a sequence. A sub 1 is 1. A sub n plus 1 is 4 minus a sub n, and that's for n greater than or equal to 1. And it says determine whether the sequence defined as follows is convergent or divergent. So if we write down a few of the terms here, just write down a few of the first term is 1, a sub 1 is 1. The next term is 4 minus 1, because it's 4 minus the previous terms, that's going to be 3. And now it's 4 minus the previous term is 3. So it's 4 minus 3, that's going to be 1. And then it's going to be 4 minus this term right here, right? So 4 minus 3. So 4 minus 1 is going to give us 3. And we're going to get 4 minus 3, and we're going to get back to 1. And this is going to be 3. And we have this sequence right here, and it says determine whether or not this sequence is convergent or divergent. Well, that sequence is not going to converge. It alternates between 1, 3, 1, 3, 1, 3. We've seen this sequence before, right? This is very similar to one of the problems we've done earlier, where we said if n odd, then we want 1. Right? Because that's A1, A3, A5. And we said if n even, then we want 3, because that's A sub 2, A sub 4, and A sub 6. And our observation there was 2 is between those. And so we said there that A sub n was going to equal 2 plus, and we either wanted 2 minus 1 here or 2 plus 1 here. So we said 1. And if we make this an n, does that work? And let's check it. If n is odd, we put a 1 here. Oh, obviously, we don't want that to be a 1. We want that to be a negative 1. 1 here, negative 1 to the first is negative 1, 2 minus 1, 1. If n is even, like 4, then this would be negative 1 to the fourth. That's positive 1. 2 plus 1 is 3. 3. So this is our general term, right? This is very similar to the problem we did earlier. I think it was problem number 10. So it says determine whether the sequence is convergent or divergent, and it's divergent because as n goes to infinity, we do not have any indication as to whether negative 1 to the n is going to be negative 1 or whether negative 1 to the n is going to be positive 1. So we're just going to keep alternating between 1 and 3. So this is divergent. Part B, this was part A. Part B says, what happens if a sub 1 is equal to 2? Well, if a sub 1 is equal to 2, and we write down a few terms here, a sub 1 is 2, then our next term is going to be 4. I've already written the answer down, huh? The next term is going to be 4 minus 2, that's going to be 2. And then the next term is going to be 4 minus this 2, and that's going to be 2. And then the next term is going to be 4 minus this 2, and that's also going to be 2. And then we have a convergent sequence because our sequence is 2, 2, 2, 2, 2, 2, 2. So our sequence converges. All right. That will complete our video on section 8.1.